Now, to summarize these two examples and compare them, we have the heat conduction problem on the left side and axial loading problem on the right side. We have the governing equations for heat conduction problem as d square t by dx square is equal to 0. Governing equation for axial loading problem is d square u by dx square is equal to 0. And it is interesting to notice how similar the mathematical formulations are, even though these two problems are quite different. And we have solutions which are called as closed form solutions or analytical solutions. For both these cases. Also notice that for the heat conduction problem, at both ends we have Dirichlet boundary conditions, that is, we specified the value of the dependent variable temperature. And for the axial loading problem, we have specified the value of dependent variable only at the left side, that is x equal to 0. So that is the Dirichlet boundary condition. Whereas on the right end, that is at x equal to 12, we specified the derivative of the dependent variable. So this is known as Neumann boundary condition. Okay. What I've tried to explain through these two examples of boundary value problems is that I have tried to explain the important terms which is associated with these kinds of problems, like governing equation boundary conditions, Dirichlet boundary conditions, Neumann boundary conditions, solution, closed form solutions, analytical solutions, all these terms. Now we can formally define a boundary value problem. Boundary value problems are those which one or more dependent variables satisfy a differential equation everywhere within the domain of independent variables and satisfy boundary conditions. I think I have explained all these terms in yellow, so you can understand what this definition means. One thing is domain. I think I forgot to explain that. Here, domain of independent variables means here the independent variable is x, and x can take values from 0 to L. So the domain means all the values between 0 and L. So that is the domain. Now, if you see the two examples that we have seen, the geometry or the problem was simple, so we were able to obtain closed form analytical solutions. But a real life problem, the geometry is complex, the loading is complex, and it is difficult to obtain analytical solutions or closed form analytical solutions. Now we can answer why we have to use finite element analysis for boundary value problems. First reason as specified is closed form analytical solutions are difficult to obtain when the geometry and loading becomes complex. So in order to solve those problems, we need to use numerical techniques and find approximate solutions. We have already used numerical techniques to solve these kinds of problems in heat transfer, 2D heat transfer problems using finite difference method. So finite element analysis or finite element method is also a numerical technique which gives approximate solutions with reasonable accuracy. So to summarize this, we have defined what is a finite element analysis. Also, we have seen where this finite element analysis is used and why the finite element analysis is used. Also, we have seen or familiarized with the basic terms associated with boundary value problems. I think this is a good place to stop this session. In the next video, we will see how can we apply finite element analysis to boundary value problems.